All right, so now that we have gone over the implementation plan for Part 5, it is time to get it coded in. So, Logan, let's go ahead and jump back over to Visual Studio Express.
All right, back into Visual Studio.
And let's start out with, let's do some constants. Now, we've already said that we're going to need a base speed and a speed variation. We've already set fields up. Let's go ahead and use some constants to hold numbers in an easy-to-get-to place so that we can tinker with base speeds and variations.
Exactly. We have fields to hold those, but we haven't defined what they are yet. So we'll define those up at the very top of our game class.
Okay.
I'm going to jump in right below player, and I'm actually going to comment in a section for enemy. So these will be enemy properties, and they will consist of two constants. We'll have both of these be floats, and the first be enemy base speed. And enemy base speed is going to be set to 3. The next, the second const float, is going to be enemy speed variation. And enemy speed variation is going to be set to 1. And that's the only thing that we'll have for properties for the enemy. Now, one thing I do need to set up is a texture for the enemy. So I'm going to jump down to the textures section, duplicate one of the lines, and call it enemy texture. And hand in hand with that, we can jump down to load graphics content and load in the actual asset into that reference. So we'll copy, I'll just very quickly copy one of the lines so that I can change it to enemy texture, and into that load in the enemy texture asset.
Okay.
And that's it for field setup. So now two more things we want to do before we actually jump into enemy itself, and that is the utility methods that will be used. We've discussed in great depth that we're going to need get random screen position and range in order for enemies to function. So let's code those in. And as we had discussed, these are going to reside within game. So I'm going to jump all the way down to the very bottom of the game right after the draw method. So there's the end of the draw method. We'll jump down, and I'm going to put a region around these so that we can easily collapse and find them. So this region I'm going to call utility methods. And end off this region. Alright, the two methods we need are the random screen position and the range. So first, let's pick on get random screen position. This will be a public static returns a vector2, and it's called get random screen position. And get random screen position, of course, takes in an integer for padding. Alright, now we need to return a vector that is somewhere within that padded screen space. So this will be return new vector2. And the x component is going to use random. We're going to use a random.next for padding and then screen with minus padding. So we can plug in random.next, and we're going from padding to screen width minus padding. So that will take care of the x component. So we'll end off the call to random, throw in a comment, and then we'll jump to the y component. And for the y component, I'm going to jump down one line and then tab over a few times, and then pretty much repeat, but using height. So this would be random.next from padding to screen height minus padding. End off the call to random, end off the call to new vector, and that's it.
Perfect.
Alright, so let's move on to range. Range is once again going to be a public static method, and it's going to return a float. And of course the method name is range. Now range is going to take in two floats, a float for minimum and maximum. So here is our float min and our float max. Alright, once again, we have covered all of the math to this on the whiteboard, so I'll simply type all of this out, where we're going to return the result casted to float, because we're going to be using next double, as seen as random.next double, and I can even hover over this just for a second to prove what you had said on the whiteboard. Returns a random number between 0 and 1 as a double. So there's next double. We take in no parameters to that call. So there's our range of 0 to 1. Now we need to multiply that by our desired range, which is max minus min. And then, of course, we want to offset up to min, and that gives us our final result. So before we move out of game, let me build and make sure that I haven't induced any errors. But I have not. The build has succeeded, and all we have are warnings.
Okay, very good.
So now let's shift focus over to enemy.
Okay.
Inside of enemy,
Time
what
to
do we want to pick on first?
Set random move.
All right,
I'll kind of follow the order I presented things.
Okay, let's implement set random move. So the 4 things of interest: point A, point B, move time, and amount. Let's start with point A. I'll use this dot point A as our field, and we need to set that to our current position. This dot position. Very simple. Next, point B. So this dot point B is equal to, now point B is the new location, which needs to be a random location. As we've just coded that, it's in game1 dot get random screen position. Your random screen position needs a padding, but we know what we are in this case. We're coding inside of an enemy. Enemy is an actor, which has a radius. Or we can look at ourselves, this dot radius, and then we have a valid radius for this position. And now we have our point B established. So let's move on to move time. Let's set this dot move time equal to our base speed field plus some form of variance. Now I have a variation in one direction. We have a positive value that's going to be coming in from that enemy speed variation. But the whole idea of variation is that I wanted a plus-minus variation. Well, now we have range, and range will allow us to accomplish that. So let's take game1.range, and now we want a plus-minus. We know we're going to have a positive value for speed variation, so it would be the minus. Well, we could just say minus speed variation, and that will accomplish what we need. So minus speed variation to speed variation. And that will give us our overall plus-minus speed variation to add on to base speed. Alright, that just leaves amount. So this dot amount, let's set that to, well, simply 0. Because you could almost say that set random move is begin random move. To begin, we need our driver, our amount, to begin at 0, the beginning.
Go ahead and throw that in there.
And, okay, there we go. That would have been a fun compiler error.
Oh,
amount.
Yeah. Oh, one more.
Nope.
Other way, yeah. Perfect.
Hey, there we go. If you try randomly, eventually the end will land.
That's right. That's what I live by. Okay, so now that we have that in place, let's go ahead and jump down to update and make this guy move.
All right, so here's update. Let me jump above the call to base.update, and let's see what we need to do. First is a check, because we've established a move time, but we haven't guaranteed that base speed and speed variation are valid. So let's do that check before we attempt to move. So if the move time is less than or equal to 0, then we have an invalid move time, and we need to recall set random move. So we'll put in a call to this dot set random move in the hope that we may get a better value. And then we need to move on to the movement itself, where we need to increment amount. So this is simply done as amount plus equals, so incremented by, well, we need game time. Game time is a double, so I'm going to cast to a float, since amount is itself a float. We're going to be looking at game time, and the part of game time we want is elapsed game time, and we would like elapsed game time in total seconds. Now we need to take that and then divide it by move time, so that we allow move time to affect the overall amount incrementing. So divided by move time, and that's it. That will take amount and set it appropriately based on seconds passed and the desired move time that we've specified. So now that we have an amount and everything else locked down, we finally have an end. Once again, I'm just going to start hitting build every time.
It's okay, because you know what I kept doing with amount when I was jotting notes down earlier? I kept leaving M off. I just did one M. So don't worry, I don't feel bad.
Should have called it percent or something else that I could spell. But now that we have everything locked down, we have all of the values we need to feed to smooth step. And if we can access smooth step, we can set our position. So let's take our current position and set that to the new position. The new position is going to be given by vector2.smoothStep. SmoothStep needs to take in 3 things. A position is a vector2, another position, and an amount. And we have all 3 things. We have a position as point A. We have another position as point B. And we have an amount. This dot amount. Hey, look at that. IntelliSense will fix the spelling. And there we go.
Oh, you spelled it wrong to begin with, then, if Intel.
Oh, that's why I wasn't getting compiler errors.
That's why it keeps doing it, yep.
All right, here we go. F2, let's refactor. Amount. There we go.
Beautiful.
And if I have anything left, it should now be fixed.
Excellent.
Yeah, good catch on that, because I was happily going to just leave it spelled. It's like, intelligence said it's right, it must be. Surely it couldn't have been spelled wrong.
It would have just blown your mind if a second later I'd have been like, hey, that amount's wrong. That would have been really funny, actually.
That would be a serious double take.
Okay, so now that we've got this guy's settings, that's position.
Now we need to account for what happens when amount reaches its final destination, the end, or a value of 1. Let's do that as a check, so we can see if the amount, this dot amount, is greater than or equal to 1. If that is the case, we've reached the end of this move, and we need to begin a new one. So that would be a call to this dot set random move, and we'll begin a new move.
You know what's funny? We weren't going to mention this, Logan, but I'll go ahead and say it anyways. If we have anybody that's real slick out there, they might be thinking, quick question, why are you checking for this here after the position? Because what if you went over just a tad? Well, you just used that right here. Oh, it's no big deal. We're still going to be at point B. It's not like we're going to push past it. I mean, we're dealing with such a small number. I mean, small.
And not only that, Smooth Step gracefully handles any overage, because in using this, it has given no problems up to this point.
Yeah, absolutely. This won't cause any problems. And I just wanted to point that out real quick, that for explaining purposes, it works real good to say, look, find an amount and use that as our driver in Smooth Step. Now, did we go past it? If so, reset.
And if you want to correct that just to feel warm and fuzzy about not going over 1, you could restructure the if statement so that the if would come before the setting and then set it up appropriately. But since it's been proven not to break in the past, then I'm going to leave it alone since the code will simply flow more
Oh, absolutely. Like I said, once again, you're not going to see a difference. That's the bottom line. Okay, so excellent. I just wanted to point that out. All right, so now that we've got that in there, let's see, what do we want to do next? Well, gee.
That's the heart of the method.
Yeah, it sure is. So let's make an enemy and try it out?
Yeah, I don't see why not.
I don't either.
Let's jump. Let me build, make sure that I haven't done anything.
Nothing blows up. Well, that's a good sign.
And aside from fewer warnings this time, everything's good. All right, let's go to game and let's make an enemy. We have been making all of our test actors inside of load graphics content, so that's where I'll return. Let me jump right before I make the player, and let's make an enemy as new enemy. Now, of course, we need to satisfy the constructor, so we'll give it a texture. We'll give it a base speed, enemy base speed. We'll give it enemy speed variation. And there we go. So let's try this.
And wait, and he got to point B. Notice how he slows down right as he starts to get to the point and speeds up out of it. That's the result of using Smooth Step.
So it's almost like he starts in a stopped state. And he slowly accelerates into a speed, then decelerates to another stop, and then begin to move over. That gives a nice, smooth, flowing movement instead of hard-edged movement.
It really
which,
does.
if you want, we could actually show. We had talked about how linear would create kind of a hard angle or hard bounce-like effect. And we could show that, because another option would have been to use vector2.lerp, so linearly interpolate between point A and B, and that would give a result like this.
Now watch him very carefully. As soon as he hits, he's going to bounce off of it.
So no acceleration, no deceleration, just a very quick hit every time the end of a move is hit.
And that doesn't look nowhere near as nice.
It gives a much more sporadic feel. I mean, it's there if you want to set it up like that, or if you want to have some other type of actor in the future, but I just kind of like the smooth, ease in, ease out look. So, I mean, that's what linear would have looked like, but we had opted to go with Smooth Step, so that we get the nice ease in, ease out flowing motion for the enemy.
I like it. And we see that everything's working right. Not only is he going to different random places on the board, he's also going about it at different speeds each time. So that's working quite nicely. All right, well, that's fantastic, Logan. So I guess the next thing what we can do is go ahead and create the add enemies so that we can put a whole bunch of them in.
And let me demonstrate one thing really quick, because you might be thinking, since this was rather simple, this one line created the enemy, why couldn't we just do that in a loop and have lots of them? Now, of course, it may be apparent that we're not getting the random, but let me show the effect of what if we had lots of enemies without a random placement. I'm going to throw down a for statement really quickly, and inside of that for statement, I'm going to create 20 enemies. So all I'm going to do is move this one line inside of a loop.
But Logan, they're all going to fan out from 0, 0.
Yeah, but it looks cool. So there we go.
Now they're all going to go random all over the place.
After that first move, everything looks correct. The problem is they all spawn out of the corner. And while cool looking, that wasn't the desired effect. We want a field of enemies to start already placed.
Exactly.
So this is why we're going to go in and create a method to handle this for us.
But it did look cool.
All right, so
it's like a very small little particle engine for just a second.
Sure. And the more enemies, the cooler it looks.
Okay, so yeah, now we're going to do the add enemies so that we can add a whole bunch of them.
All right, so one last time, let's jump over to the enemy class and let's implement add enemy. So here we already have the skeleton. So all that's left is the for statement and a couple lines of code. So for statement, almost exactly like I had done back in game.
Except for our length is now num enemies.
So let's plug in num enemies. And then inside of the loop, we need to first create an enemy, which I'm going to save to a variable. So I'm going to make an enemy variable and initialize that to the actual enemy. So new enemy. Here we're going to plug in some parameters taken in as texture, base, speed, and there we go, and speed variation. So that will create a new enemy. Now, since we're still holding that reference, we can turn around, take that enemy, and set its position. So position equals game1 dot get random screen position. And again, we have an enemy, so we can plug in that enemy's radius for the padding.
Excellent. So now we can randomly distribute any number of enemies.
So we can jump back to game now and use that new method. Let's wipe out our temporary for loop here. Bring this line back, and instead of new enemy, instead what we want is a call to enemy dot, and I grabbed texture somehow, enemy dot add enemies. Now we need to change this out because we need, let me bring up IntelliSense, Control A, or Control K, Control P, num enemies. So let's go with 20 once again, and then everything else should pan out. So here we go.
20 of them randomly all over the screen.
So an instant field of enemies already placed, so we don't have any of that fan-out effect from a corner.
Outstanding.
All right, so that's working. I'm going to drop this to 5 now, because for later testing purposes, I want to have few enough enemies so navigation is possible.
Okay.
So there's a smaller field of 5 enemies.
Sure. All right, now with that out of the way, the next thing we're going to do, so the heart of this entire section is really taken care of. Now let's see about implementing that scale functionality we put in place a couple sections back. Let's get it to where we see these guys scale into existence now. So they're going to start out with a scale of 0 and scale in.
Okay. So back to enemy briefly. We're going to do this. Let's do this from the constructor because the idea is that the enemies have a scale in effect. So we'll do that upon creation. So up in the constructor, we're going to set the initial scale and then set a start scale animation, where we do something like this dot scale starts at or is equal to 0. Then we turn around and make a call to start scale. And what we want to do is start a scale up to a value of default, or 1, and we want to scale over a given amount of time. Now if you remember, we have skeletoned in this constant for enemy scale time, so let's plug that in. So enemy scale time, and we can try it out. So the enemies scale into existence. But let me slow that down so we can see one other thing that's happening. Let me change this to 2.5 seconds. So there's the enemies scaling, but wow, look at that. They're moving while scaling, and what we wanted was to have the enemies stay in place until their scale in effect is complete, then begin moving.
That's right. So we need to go ahead and set that up.
Another thing that we wanted to do, I guess we can do these hand in hand, is we also wanted the is harmful property, because the idea was also that enemies are not harmful until they have scaled in fully. Exactly. What this does is give you kind of a grace period where if a cell has just died and an enemy just starts to spawn out of it, it doesn't immediately kill you, because you could have a tiny speck of like a very tiny enemy that you couldn't even see kill you, and it's just not fair.
Exactly.
So let's plug in this property for is harmful. I'm going to jump up right above the constructor. We'll put down a public property. This will be a boolean, and we're going to call this is harmful. And all is harmful is going to do is kind of act as a wrapper to scaling, because whether or not it's harmful is all based in scaling. If we're scaling, we're not harmful. So we can do just that. Let's put in a get accessor, and let's return scaling, or is scaling, except let's invert it. So return not this dot is scaling. So that way harmful is whenever we're not scaling.
Right.
Now this means we could use this for something else. The other thing that I want to have happen is have the enemies not begin moving until they are harmful. So that way a moving enemy is a harmful enemy.
That's right.
So let's jump down to update, where we are actually performing the move, where amount and position are being set, and let's put those inside of an if statement. So we can say if this dot is harmful, then we move, and otherwise we stay still, which will give us this visual effect. So there's some enemies spawning, but they're still staying, and then they begin moving after a scale is accomplished. So with that working, I'm going to jump back up, set this enemy scale time back to the desired half a second, and there's our effect.
Nice.
And really, I think that was everything that we needed to add to the enemy.
So we have got a moving system in place. We have the ability to randomly distribute enemies throughout the scene on spawn. And they scale up from 0. They don't move while they're scaling. Once they reach a scale of 1, they begin moving. They accelerate into their move, or into their constant track to the new location. Once they decelerate as they come into that location and turn around and start accelerating out of it to a new location, they just keep, wandering around the screen. So it's doing exactly what we set out to accomplish at the beginning of this section. Is there anything else you can think of?
Nothing comes to mind. Everything has worked, aside from the spelling of amount. Everything has worked exactly as planned.
All right, so then that's going to wrap this video up, and in the next section we'll start getting some player-enemy interaction going on. So thanks a lot, guys.